pleasure to introduce this morning's keynote speakers. Tim Berry is the head of manufacturing and quality at JetZero. Tim's experience encompasses high-rate, low-cost production of aerospace hardware, advanced manufacturing technologies, and quality management systems gained through working at innovative companies such as SpaceX and VAST. At JetZero, Tim oversees manufacturing and quality teams working to build the factory of the future that will support full-rate production of their blended wing body aircraft. Kevin Brauning is the head of JetZero Structures Engineering. Kevin's background in design manufacturing of large monolithic composites, he has supported a multitude of new development programs for commercial and defense customers. At JetZero, Kevin oversees the airframe structures engineering team, working both the demonstrator and production aerostructures. JetZero's structures and manufacturing leadership provide a summary of the industry landscape developments that have positioned the aerospace industry for change. Please welcome to the stage Tim Berry and Kevin Brauning at JetZero.
Good morning, everybody. Like Tom said, my name is Kevin Brauning. This is my colleague Tim Berry, and we're here to talk to you a little bit about the future of aerospace. Tom introduced us, so I'm going to just blow past these. And I'm going to start off with a bit of a downer. Our industry as a whole has a big challenge in front of us. Our biggest challenge, as we see it at JetZero, is carbon emissions, climate change in front of us. Today, we're looking at just shy of 1 billion tons of CO2 emissions annually as a result of aerospace. That's set to double in the next 25 years. By 2050, we're looking at 1.8 billion tons of emissions annually. In addition to that, airlines have committed by 2050 to be on a net zero emissions standard. So what does that mean? What does it take? It's more cost to all of us. Your flight is going to get more expensive. There's a lot of upstream investment that has to happen, both in infrastructure to develop sustainable aviation fuels, storage of hydrogen. It's a substantial investment from the public at large, and then stakeholder buy-in as a whole. This requires government support, it requires industry buy-in, and a substantial level of change in order to get us to a net zero position. Thinking about that from an industry impact perspective, I want to take a look at just a few events over the last couple of decades that were hugely impactful to our industry as a whole. 9/11 was roughly a $150 billion impact to aerospace. COVID-19 was about $250 billion. And if you were to look at a net zero 2050 initiative, approximately $4.6 trillion of investment is what we expect that to take for us as an industry to get there. And in addition to that, fuel costs go up 2 to 3 times in perpetuity. That is profoundly impactful to all of our futures, and we've got to do something about it. Aviation as a whole has an innovation problem. Start with the Wright Flyer in 1903 and progress 60 years and you arrive at the design onset of the 737-100. There's a lot of steps that it took to get there, and we're going to walk through those together here in a moment. But since 1963 to today, another 60 years have passed, and we're still flying tube and wing aircraft that look largely the same as what they did back in 1963. So how did we get from a Wright Flyer to the 737-100? There were inflection points on the way. Biplanes were the standard airplane shape for many, many years. And then in 1934, the de Havilland DH-88 Comet was introduced, which moved from a biplane to a monoplane design. Another important inflection point was moving to pressurized fuselages. This made flying more comfortable for the general public. Range was increased. And within just a few short years, most passenger aircraft were pressurized. Another inflection point was landing gear. So on the left, the tail dragger landing gear configuration was very traditional back in the 1930s. As an industry, we began moving to a tricycle-style landing gear, which is on every commercial aircraft today, in 1942 with the Douglas DC-4. That conventional gear on the left doesn't look so conventional anymore. And then here's a really big one. It's the move from piston aircraft to jet aircraft. Range increased, speed increased. This is what we would call a majorly disruptive event. If you look at the airplane on the left, it looks tremendously outdated just a couple years after its introduction, and really disrupted the investment that was made in that platform. So what did it take for them to get there? These are all inflection points. They were all disruptive to the industry, but there's a big lag between the invention of that idea and when it was commercialized and the public is seeing it for the first time. That cantilevered monoplane, it was invented in 1915, and the first commercial aircraft didn't see it until 1934, almost 20 years. Pressurization, again, almost 20 years from 1920 to 1938. Tricycle landing gear, 1908 to 1942. That's 3 decades of lag between the introduction of a technology, when it's invented, and introduction to market. And then finally, the jet engine, 1935 to 1949. All of these combined have big lags with big impacts in terms of overall performance of the industry. So what's next? 1963 to 2024, 60 years. What's the next 60 gonna look like? So while commercial aviation has been a little bit stagnant, the defense sector, they're ahead of the curve, they're ahead of us. Flying wings have advanced flight controls, fully buried engines, no passenger cabin, so not exactly relevant for air travel for the general public. But they continue to innovate at a very, very rapid pace compared to what we're seeing in the commercial market. So speaking of technologies that are matured but not yet commercialized, keep in mind in the back of your minds the gap between invention and commercialization. We're going to circle back to that here in a little bit. But the blended wing body is a concept that the JetZero is continuing to mature, and we believe this is a big contender for that next inflection point. So just going through some of the faces on here, Elon Blaine, Mark, Bob Liebeck, they're all with JetZero right now. They've been maturing this technology of a blended wing body since its inception in 1989. That maturation has come with substantial backing and investment from folks like NASA, from McDonnell Douglas, Boeing. Many companies have invested in this inflection point over the preceding 3 decades. So what's the benefit? Not everybody's familiar with a BWB, and not everybody is familiar with aerodynamic concepts. I sure wasn't an aero expert before joining JetZero, and our aerodynamicists have schooled me over the last year and a half. But in a traditional tube and wing aircraft, the tube adds no lift. Everything is coming from the wings. That seems pretty obvious to almost anybody. With a blended wing body, what that's doing is it's distributing that lift across the entire body, balancing the inertial loads. So there's an elliptical profile to that. It reduces the cantilever. And what that means from a composite structures design standpoint is that I can use less structure, less material weight, and we get into a virtuous circle of less weight, less thrust, more efficient airplanes. One last benefit that we see as a benefit of the blended wing body is an eventual path to hydrogen. We know it's not the next inflection point, but it's an eventual inflection point for our industry. And in a tube and wing, envisioning how a hydrogen tank fits on that structure is challenging, to say the least. Our forecasts show that about 2/3 of the seats get converted to hydrogen in a tube and wing in order for that aircraft to fly the missions that they're on today. On a BWB, there's ample volume in the sides, and we can change that number from 2/3 down to 1/3 instead, and still get 3,000 nautical miles of range. So as a whole, we believe the shape of aerospace is changing. There's a lot of interest in BWB or BWB-like aircraft. You can see our platform on the left, and many other companies are investing in this space in both research, hardware development, test articles, in terms of flying drones. So how are we going to get there? What do these new shapes and new platforms, new structures require? First and foremost, and I think it speaks well to this room, is advanced materials and processes. We've got to begin treating composites differently than we have been, and adopting a new mindset as engineers in terms of what this next inflection point takes. Highly capable machines, automation equipment, is going to be big in order to have this be a meaningful impact. If we're going to do anything, we're going to have to do it at rate in order to take a bite out of the 2050 net zero challenge. Novel joining techniques is another one. Tim is going to talk about this extensively here in a moment, but we've been doing things in a very old school fashion for many, many years in terms of how composite structures come together. And last but not least is taking a first principles approach to structures. Reassessing from the ground up, what does the structure want to look like, how does it want to be built, and not necessarily relying on historical systems on how things have been done before. So with that, we're going to look at one of my enabling technologies that's a big consideration for myself and my team, and that's the composite airframe on a BWB. One of the clearest challenges that we have in front of us is that our fuselage is not cylindrical. Cylinders pressurize really easily. Rectangles don't. What that means for me is that I need to come up with a pressurization system that withstands a non-cylindrical shell and all the stresses that induces. In doing so, I have to maintain an aerodynamically smooth surface, or those aerodynamicists that I spoke about previously are going to be a little mad that I've forgotten the lessons they taught me. And I've got to have a light and damage tolerant structure because the airlines don't want something that they have to baby day in and day out. So one enabling technology that we see is stitching of composite airframes. So in that rectangular pressure vessel, it's not just stretching like what you would see in a traditional composite laminate. It is stretching and bending, developing interlaminar shear. We need something through the thickness in order to resist that interlaminar shear. And one of the solutions we've been investigating is stitching. So a single-sided sewing head would stitch fibers through the layers, helping prevent delamination. Dry fibers are the ideal approach for stitching because you can't stitch through pre-preg without gumming up the thread. And it's a fast and reliable process, relatively speaking. There's opportunities for both structural strength here as well as manufacturing preforming and enabling throughput in our factory. So one look at an approach to stitching of composites is this scheme that you see here. So in a cylindrical pressure vessel, these cross sections that we're looking at are something called Perseus. It was invented by NASA a couple decades ago in conjunction with the Boeing company. Cylindrical pressure vessels, like we talked about, are just stretching, not stretching and bending. A stringer would develop peel stresses right along the edges and has to be resisted. So if you take this as a building block, begin stitching lines along the stringers, along the frames, sew tear straps in, what you get as a result is a very lightweight, damage-resistant, thin composite structure that can be developed in very, very large sizes. So taking that idea, there's been a substantial amount of NASA funding. They've published about 100 different papers that you can go find online and read about the Perseus scheme. There's flying hardware that uses a similar architecture on the C-17 landing gear doors. And then in the right-hand side of this picture is a demo box that was done at the Colts facility, representative of a BWB. That they built at full scale and tested. So with that, I'm gonna pass over to Tim Berry, and he's gonna give a little discussion on manufacturing approaches for blended wing bodies.
Thank you. Hello. So like Kevin said, the industry is ripe for change. If you take a look at the photo here, you've gone through all the trouble of building a composite structure only to then treat it like black aluminum and shoot 1 million fasteners through it. Every single one of those fasteners, as I'm sure you're all aware, has to be drilled, reamed, countersunk, hole checked, gap checked, and there's inspections spread throughout that entire process. So a lot of labor, a lot of time, a lot of risk of defects as those fasteners are being installed. The article that was tested at Colts proved that the potential for fastener reduction is there, and the juice is ultimately worth the squeeze. So as Kevin said, they took BWB section and they built a test article using the Perseus concept. And then they tested it to its limits at the Colt facility, and it passed the full test campaign. The chart on the right-hand side shows the reduction of fasteners that are possible. So going from a traditional aluminum, bolted structure down to a pre-preg structure, but then still having to shoot a bunch of fasteners and bolts and things like that through it, resulted in a reduction. But Perseus took that reduction even lower still, and JetZero believes that with our production architecture, we'll be able to reduce this even more considerably. Another great part about our approach, or the approach of stitching in general, is that it allows you to reduce part count. So from my time at SpaceX, one thing that we learned was that deleting parts is the best thing you can do. A deleted part can't fail, it doesn't cost anything, you don't have to inspect it. So if you can eliminate the part, that's always the best choice. So if we can delete a lot of the parts and simplify the piece parts that we're using for the layup, then ultimately it's much easier to scale and reach production rates. And so on the left-hand side, you'll see there's a copious amount of parts in this 757 diagram. A lot of them are unique, machined, they're molded, a lot of mating, fastening, drilling, metal shavings that you have to clean. And so on the right-hand side, with the Perseus approach and ultimately JetZero's long-term production approach, there will be a much more simplified piece part count. And it's much easier to place all of the subcomponents into the structure. So currently, as I said, it's a lot of precision machine parts, precision assembly, precision fastener drilling, fastener driving. So what we're looking at, and what the industry as a whole should look at, is replacing all of the precision fasteners that are in composite assemblies with stitching. You have non-precision processes throughout most of the production cycle until the very end, where you have precision in the coat curing utilizing a simple mold. I'm sure all of you are pretty intimately familiar with what resin transfer molding is, but for those of you that aren't, comparably to using prepregs, RTM gets you out of having to have very large autoclaves, which often can be the most expensive line item on CapEx for producing composites. Prepregs also require a lot of cold storage. They have out life requirements, and ultimately are just harder to handle and deal with. So using resin transfer molding in a simple mold allows you to eliminate a lot of those handling problems, a lot of the CapEx and equipment that you need for post-processing, and it allows you to essentially stitch together the entire structure before you infuse the whole thing at the same time. Another innovation that I think is key to the aerospace industry moving forward is hybrid machines. So instead of having a long production line that has one cell that does one type of technology or manufacturing process, where effectively if that machine goes down or a part or an assembly dies in that lane, then your entire production line is gummed up. Instead, you can focus on a multitude of machines that can do uniform cell work content and effectively can go and swap out heads for each of the processes that they're doing. This also is a cost reduction opportunity, because instead of having to duplicate the motion system, the rails, the gantry, all the moving parts other than the head, you can have everything on a single platform that does a multitude of different processes. Given that all the work cell content is uniform, it makes it a lot easier to scale up and increase production rate. Another innovative technology that folks should look at incorporating is continuous fiber printing. So this is taking a single or a few fibers and depositing them in a polymer matrix to create unitized structures. This opens up the potential with composites of doing topological optimization, only putting material where you actually need it, and not a traditional wing box structure, which would be a lot of bolted, bonded sheet metal components together and maybe overkill ultimately. It also enables functional integration of sensors, which I'll talk about on the next slide, and ultimately will reduce weight and part count. So we've made a lot of innovations in the metal printing space, especially in my time at SpaceX. I ran the metal additive department. But I think that innovation now needs to make its way over to the composite space as well. Yeah, another benefit of continuous fiber printing is for structural health monitoring, what we would call an aircraft nervous system. So current state of the art on most aircraft for structural health monitoring is a bunch of strain gauges that are applied to the skin. There's miles and miles of wires that are run and a lot of management. They easily detach. As someone who has installed a lot of strain gauges myself onto rocket fuselages, I can attest to just how much labor this takes and how terrible of a process it can be. With continuous fiber printing, you can swap between a fiber and, say, a copper wire or a glass fiber or a fiber optic cable that's then impregnated into the actual base material and allows you to have a smart composite structure without all the required labor of placing the strain gauges individually. Another innovation that a lot of folks are investigating and some have already taken up is thermoplastic welding. Kevin and I were lucky enough to visit a DLR center in Augsburg, Germany, and see their innovative processes for thermoplastic welding, which really blew us away. I would highly recommend you go on YouTube and look up the MFFD, which is a fuselage demonstrator that was produced by DLR in partnership with GCAN Fokker. All of the stringers that are on this structure and all the frames and all the cleats and the skin are all thermoplastic, and all of the stiffening structure is attached with thermoplastic welding, whether it be resistance welding, induction welding, or ultrasonic seam welding. It enables a strong homogeneous bond without having to use a lot of epoxy bonding or millions of fasteners again. I've heard some folks say, oh, well, the FAA will never certify a thermoplastic weld. Well, guess what? It's actually currently certified and flying on a lot of aircraft already. So it's a technology that's rife to be incorporated into new aircraft and also for replacement parts for existing aircraft as well. Folks have built things, like I said, as large as a fuselage or a demonstrator A320 bulkhead that was made by Airbus. Now I'll go through a few lessons that I learned from SpaceX that we're applying to JetZero. So we really want to bring the disruptive, innovative energy of SpaceX to aircraft manufacturing. As Kevin said, it's really a focus on first principles, getting down to the base level of what you absolutely have to do for the part versus what's a nice to have, or any superfluous processes that don't need to be in the production process. So first and foremost, Elon really drilled into our brain something that we call the algorithm. So it's a 5-step process for design for manufacturability and ultimately optimizing your design overall. So the first step of the algorithm is challenge requirements, or as Elon would say, your requirements are definitely dumb, you need to make them less dumb. So you start with challenging the requirements, right? The next step is to delete the part or process step. Now, a lot of people are familiar with deleting parts. As I said before, it's great. They don't fail. They don't cost anything. You don't have to check them. You don't have to install them. So you want to delete as many parts as possible. A lot of people forget the other half of that, which is also to delete process steps. An example being, you clean something, you do a bunch of work to it, and then you clean it again. You don't have to clean it the first time, just clean it at the end, right? So looking at the entire value chain of each of your parts, each of your assemblies and components, and eliminating as many process steps as possible will ultimately increase your production rate, lower your labor, and reduce the chances for defects. Once you've really boiled down to what the base level design is that you're working with, then you take a look at opportunities to simplify or optimize the design even further. Once you've optimized or simplified your design and you really have something that you're happy with going into rate production, you can accelerate. You can add more capacity, more work cells, and ultimately quicken the pace that you're producing the components with. And then the last step is to automate. And the key here is that most people start at step 5, automating, and they automate processes that never should have existed in the first place. And this was a personal hard-won or hard-learned example at Tesla, where they effectively automated a bunch of processes that they ended up deleting later, and they figured out that they didn't need. So it's important that you actually work the algorithm in this order, and you only automate once you've really gotten down to the base level requirements that you have, and a part that ultimately demands the automation being needed. But you're never done. You don't run this once and that's it. You constantly are iterating. You're bringing in new talent, new mindsets, new ideas. You're finding more ways to recursively run the algorithm and always improve your designs by leveraging continuous improvement. So there's some real world results here that just show just how effective the algorithm can be. So on the left-hand side, you'll see that was Raptor 1, the first iteration of Raptor. It was 185 tons of force, and it was pretty considerably heavy. I mean, you can see the Christmas tree of sensors and turbo machinery, tubing. Iteration of the algorithm ultimately produced a cheaper, lighter, higher performance product that was simpler to manufacture. So the current iteration of SpaceX Raptor engine is Raptor 2. And if you look from Raptor 1 to Raptor 2, not only did it get simplified and did it get lighter, but actually they were able to increase the thrust considerably as well. So they got a better product that is lighter, cheaper, and easier to operate. Looking ahead, SpaceX's Raptor 3 engine, which Elon recently briefed in a company talk, is lighter still. It's even further simplified, just looking at it, and it has 50 tons higher thrust. An equivalent engine from another rocket engine manufacturer can weigh up to twice as much as this engine and produce the same thrust. So this really just shows the optimization potential that's available by running the algorithm. So Kevin went through this slide earlier that showed the maturation process for each of these technologies. JetZero is very close to the finish line of maturation of PWB technology, which, as we said, has been in work since the late 80s. Our first principle solution to solving the emissions problem and the fuel efficiency problem is just the shape. We are not doing anything crazy. I worked at a company called VAST doing commercial space stations, which is a very risky business, if you can imagine. And what I really appreciated about JetZero when I came is that the shape is the new technology. Everything else is currently certified flying FAA systems that we're utilizing. So really our first principle solution is just taking a new look at the shape and implementing it. Finally, just to give an overview of JetZero's variants and scale up, we have already flown a 4% scale, what we call foamy aircraft. We are about to fly a 12% scale Pathfinder aircraft, which uses dynamic scaling to give us an initial sense of our aerodynamic performance. We're currently working under a U.S. Air Force contract in partnership with Scale Composites and Northrop Grumman to build a demonstrator, full-size demonstrator aircraft, which will fly for the first time in 2027. The military's interest in the blended wing body is as a tanker, as a next-generation tanker aircraft. Entry into service of JetZero's commercial variant, commercial jetliner, is targeted for 2030, with other variants following closely behind, and eventually a hydrogen variant as well. We believe that the simplicity of the manufacturing approach we have, coupled with the innovation of the technology and the fact that we can do many missions on the same airframe, will ultimately yield a very sophisticated platform that can support aviation now and into the future as well. Thanks.